Very good morning, students. Welcome you all for a lecture 10 on signals and systems. Today's topic that we are covering are elementary signals. We studied about two elementary signals in the previous class, and in this class, we are covering up the subsequent elementary signals. So, to summarize what we done in the last class, we could understand what are sinusoidal signals, and then we also understood what is the meaning of exponential signals and how it varies. Okay, we could learn these two things, and also we could derive the relation between these two things. So this was the summary of the previous session. So in this session we have three to four or two to three different kind of signal. First one is exponentially damped sinusoidal signals. We understand what's the meaning of exponential signal. We also understood what's the meaning of sinusoidal signal. Now, what is this? The combination says exponentially damped sinusoidal signal. Damped means the one which is decaying. Okay, so the meaning of this is it's a multiplication of exponential signal e of e raised to minus 80 and a sinusoidal signal. It's a multiplication of these two things. You can see here. It's a multiplication of e raised to minus 80 into sine of omega t, where a is greater than 0, because there is always a negative, already negative sign is there. So once your a value is greater than 0, this results in decaying kind of exponential. When you multiply the same with the sinusoidal signal, that sinusoidal signal gets decaying kind of. Hence, we call it as damped sinusoidal signal. For DT signal, this signal looks like x of n is equal to c into alpha raised to n, and then followed by sinusoidal signal. With some phase, you can have it as 0 also or any value also. Why alpha raised to n? You please recall the exponential signal topic that we studied in the previous class. We had, in place of e raised to 80 that we had in the continuous time signal, on contrast for dt signal we had alpha raised to n, c being the constant. To just brief you, give you some more idea on it, I've taken an example. So this example make you much of the topics clear. Here what is given is, there is a signal given, continuous time signal, a into e raised to alpha t plus j omega t. So this is a equation given where a is greater than 0, that has been mentioned. So here I think this should be capital A. Capital A. Okay. So evaluate real and imaginary components of the x of t. So this is a question. So alpha, three cases have been given. First case is considering alpha to be real, like that is alpha is equal to alpha 1. Second case being alpha is imaginary, alpha being j omega 1. The last case being considering alpha as complex signal, complex value, alpha is equal to alpha 1 plus j omega 1. In these three cases, if I substitute in place of alpha, then how to write real and its imaginary components of the x of t. That is what we are going to learn now. Okay, so let me start with a solution. The first case, let me consider where alpha is real. Let me consider alpha is equal to alpha 1. So here I take the given signal x of t is equal to a into e raised to, in place of alpha, what I need to put? Alpha 1 into t plus j omega t. So this can also be written as a into e raised to alpha 1 t, there is a plus here, dot into e raised to j omega t. This is indices rules that you have learned in your schooling. So when the base is same, so indices can be added. So it is a reverse process of exactly what I just now told. Okay, so once I have this, you know that alpha 1 is a real value. Okay, so this is a complex value, j is there. So I use a Euler's formula in order to write the real and imaginary part of it. The real and imaginary part can be written by Euler's formula. Euler's formula says that in place of e raised to j omega t, you can write it as cos of omega t plus, because here plus is there, j sine of omega t. So what do you get? A into e raised to alpha 1 t cos of omega t plus a into e raised to alpha 1 t sine of j omega t, sorry, not j, just omega t. So there is a j here, I'll write it here. Okay, so now you can easily write what is the real part of the given signal. Real part of the given signal, so considering the case 1, it is j followed by j, it is imaginary part. This is a real part, this is a real part. Okay, a into e raised to alpha 1 t cos of omega t. So this is how you need to write. So imaginary part is of the given complex signal is a into e raised to alpha 1 t sine of omega t. So this is how you need to derive the real the real and imaginary part of any given signal. Now quickly we will understand how to do the same in the same process, how to do it for b, where alpha is j into omega 1. Quite simple, quite simple. So what you are supposed to do, take the signal x of t is equal to a into e raised to, in place of alpha I'll be substituting j omega 1 plus j omega t. So what happens here? So here a e raised to j I'll take common. So what is left? Omega 1. So alpha t it is. Alpha t it is. So alpha in place of alpha, j omega 1 I have written. This t was missing. I'll write that t. Omega t, omega 1 t plus omega t. So this is how it happens. So only j component, both are complex, hence I apply Euler's formula directly here. So what happens? Cos of, so in place of theta, whatever I'm having, I'll just write it omega 1 t plus omega t plus, because here I'm having plus, sine of omega 1 t plus omega t. Okay, so A is related to both of the components. Now, if I ask you to write the real component of the given signal, so your answer should be other than J, whatever you have, you write it A into cos of omega 1 t plus omega t. Similarly, imaginary part of x of t is A into sine of omega 1 t plus omega t. That's it. This is about B. Now last thing is C. I'll utilize the space left. So alpha being the complex value. So complex value. This is what you need to substitute. Let me take the given signal here. A into e raised to, in place of alpha, I am writing alpha 1 plus j omega 1. So in place of alpha, I wrote it t, I wrote it plus j omega t. So now carefully you need to separate the imaginary part and real part here. So what I do is a into, first I'll take e raised to alpha 1 t separately. E raised to alpha 1 t, I took it separate. Dot into e raised to, whatever left I write it, j omega 1 t dot e raised to, again there is a plus, again there is a plus, this is into, okay, this is into j omega t. So now I combine the j components. This I write it here. I combine the j components. What do you get? J omega 1 t plus omega t. So this is like combination of A and B case. Now we can directly write the real part and imaginary part. Okay, so this gives you cos and sine signals. Cos of omega 1 t plus omega t plus j sine of omega 1 t plus omega. Directly I'll write real component and imaginary component. So real component is x of t. Real component of x of t is a e raised to alpha 1t. What is the real component of this e raised to exponential signal? Cos of omega 1 t plus omega t. That's your real component. Imaginary component is a into e raised to alpha 1t. I have to write sine now. Sine of omega t plus omega 1t, or else omega 1t plus omega t. Both mean same. So this is the answer for the problem that has been given to you. So we shall throw some light on what is the meaning of this step function. So we have again continuous time as well as discrete time for the step function. Continuous time and discrete time. So continuous time signal or step function is denoted by u of t, whereas discrete time is denoted by u of n. This is step function, and in some book even they use s of t, s of n. There is slightly variation between these two things. Let me tell you that. Okay, so I'll tell you what's the difference when we will be using u and when we'll be using yes. And some authors use these denotions interchangeably. I'll just give that idea. Okay, so let us start with discrete time version of unit step function. The discrete time version of unit step function is defined as u of n is equal to, it will be 1 for n greater than or equal to 0, and it will be 0 for n less than or less than 0. So the graph shows here, this is x-axis n, integer n, and starting from 0, 1, 2, 3, it will go on, and negative side. For n greater than 0 and 1 2 3 continues, it stays at 1, and for the negative values it stays at 0. This is called step function. Why it is called step function? Because at 0 it is like looking like a step. See, it is looking like a step. It's looking like a step, hence we call it as step function. So up till 0 it will stay at 0. At 1, once it reaches n equal to 0, it will take a step of amplitude 1, so hence it is called as step function. Fine. If the step function, if the amplitude is just any amplitude, a might be any value, any positive value, then we call it as a step function. If it is, if a is equal to 1, if a is equal to 1, then we will call it as unit step function, or just unit function, just unit function. So these two cases we normally use u of n as a denotion, and other than amplitude 1, if you have any other value, then normally we will be using s of n for the denotion. That's it. Remember this. Okay. So similarly, for discrete time, for continuous time, if you want to analyze, the signal looks like this. U of t is equal to 1 for any value that is greater than, or any value of t that is greater than or equal to t, and it is equal to 0 for any value that is less than 0. So here the meaning is, at t is equal to 0, it is taking a step. That's the meaning. That's why I have separated t greater than 0 and t equal to 0. Okay. So precise graph and commonly used graph. Just don't confuse between these two things. The intention of taking this precise graph is, there is a change in the value at t is equal to 0. You know, t is equal to 0 in real time. In real time, anything that changes its value needs certain amount of time, right? Anything, let it be anything. You take any practical thing in this real world, to change its value, to change something, it takes some time. Abruptly at t is equal to 0 second, nothing happens. It takes some milliseconds or nanoseconds or whatever it is. So that's why, to mark it, what I've done is I've shown slightly a slant line. This is a slant line. Slant line means there is some delay for changing the value of a signal from its point at 0 amplitude to, to the point till it reaches the maximum amplitude. That is, let us consider there is some signal called g of t, and if this g of t is having finite values only for the value of t greater than or equal to 0, then you can just write it as g into u of t, rather than rather than writing it in this fashion, g is equal to some value. Let me consider like some value, some value in the range t greater than or equal to 0 and 0 t less than 0. So rather than writing like this, from here on, I use this fashion of writing. What is that? G of t into u of t means u of t is having value 1 at t greater than or equal to 0. So if I multiply it with g of t, so wherever u of t value is 0, g of t goes to 0. That is what is the meaning here. Wherever value of u of t is 0, so your g of t value is 0 itself. Wherever your value of g of t is some value, I'm multiplying it with 1. So rather than writing in this fashion, let me use writing of signals in this fashion. So this is the trick that we use. This is how we reduce our writing effort. Okay, I hope this is clear to you. Fine. So now quickly we will take one more signal which is related to the unit step function or the step function. That is rectangle function. So rectangle function, there is again dt signal and ct signal. So here I have shown some period, some rectangular signal here. So here it is having amplitude 1 for some range, specific range, that is minus n suffix w to plus n suffix w. Rest otherwise it is having 0 values. This is 0 values. So how to write it? Write it in mathematical form. Rectangular function of n is equal to 1 in the range minus nw till plus nw. Okay, and 0 otherwise. Similarly, for rectangular function in terms of discrete continuous time can be written as so 1 in the range, I am taking range minus a to plus a, so let me write it as minus a less than or equal to t less than or equal to plus a, 0 otherwise. This is a rectangular function. Rectangular function. Remember this. Okay. So this rectangular form pulse can take any other way also. For example, just here I want to have this a as zero point 0.5, this as plus 0.5. Okay. So what I do is I will give you two signals to generate it, two step signals to generate it. Just check here. Just check here. I have one signal. I write it as u1 of t, u1 of t. The signal looks like this. Signal looks like this. Minus 0.5, 0, 0, zero point 0.5. Let me call it as x1 of t. Okay, I don't use u of t. Okay, simply it will confuse you. This is amplitude 1. It continues. This is x1 of t. x2 of t is minus 0.5, 0 plus 0.5. From here it starts. This is amplitude 1. So I'll have to use these two signals in order to get this signal. How to do it? So for that, let me just take one more slide. This is amplitude 1. So it continues. This is 0. This is time axis. And x1 of t is it is starting from plus 0.5. And let me write down that u of t minus 0.5. Okay, so just we will do some reverse engineering. We could learn about time shifting, right? In the previous sessions, we had something like u is just like x of t and some function it is u of t minus 0.5. This is u of t. U of t minus 0.5 means what happens? It is like shifting the original signal to the right by 0.5 times. So what's the meaning of this? Shift where? Shift to the right, because I'm having minus here, by how many times? 0.5 times. So that is what is done. This is taking step from 0 from at 0. So shift it by 0.5 onto the right. Onto the right. So it is being shifting to the right by plus zero point 0.5. So the same signal, same signal, I picked it and I shifted by 0.5 times and I placed it here. That's it. That's it. Nothing else. How to write the mathematical model for this equation? X2 of t, where it is starting from minus 0.5. So it is u of t plus zero point 0.5. The meaning of this is shift, because there is plus here, left by zero point 0.5. That's it. Shift left by zero point 0.5. That's it. Okay. So now coming to the original signal, that is rectangular signal I had drawn. This is a rectangular signal. This is a rectangular signal. Sorry for my diagram. This is a rectangular pulse I had considered to produce using the given signals. This is what I want to produce. This is what I want to produce. Use this x1 of t and x2 of t signals, do whatever operation possible and try to generate x of t for me. So this is x2 of t, x2 of t minus this is x1 of t. So some of the students says this gives you the x of t. Let us check. So from minus 0.5, x2 of t is having amplitude 1. Okay, so I'll take it here. I pick this x2 of t and I take it here. So it is changing the step from minus zero point 0.5 and it is reaching amplitude 1 and it is continuing. Until where it is continuing, x2 of t is continuing till infinity. But what about x of t? It should stop at plus zero point 0.5. So at plus zero point 0.5, from plus zero point 0.5, there is one more signal getting generated. That is x1 of t. And it is taking its amplitude to logic, taking its logic to, amplitude to 1. So 1 at 0.5 gets subtracted when you subtract it with x1 of t, because x1 of t's amplitude is 1 from plus zero point 0.5. From plus 0.5 onwards, this x1 of t and x2 of t's amplitude gets cancelled. It gets cancelled. Hence, it will result in rectangular pulse. So if you add it, x1 of t plus x2 of t, if you add it, what happens is from minus zero point 0.5, your amplitude is 1. From plus zero point 0.5 onwards, you are adding it. You are adding this one. So your amplitude will increase. This was 1 and this becomes 2. It continues like this. Okay, so that's why this is a wrong answer. Fine. X of t is equal to x2 of t minus x1 of t. This can also be written as u of t plus zero point 0.5 minus u of t minus zero point 0.5. This is also equal to x1 of t. So in place of 0.5, you can also write half. This is also okay. So all these means same. All these means same. Okay. So now I'll take one more example. Okay. So x of n is given as 1 for the value for the range 0 to 9, and it's a discrete time signal, and this is otherwise. Use u1, use u of n, that is unit step function, to describe x of n. Did you got my question? You have to use u of n or variation of u of n to describe x of n. So produce this signal, generate this signal by considering u of n. Okay, so let me solve it. So what is u of n? For others who have not yet got clear idea about it, just concentrate here. U of n is nothing but what? It's a discrete time signal till 0 or till minus 1 it is having the amplitude 0. At 0, it is having amplitude 1. At 1, it is having amplitude 1. At 2, it is having amplitude 1. So it continues. So this is a unit step function, discrete function. Now use this in order to generate x of n. How does x of n is looking? Let me draw that first. X of n is looking in this fashion. 0 otherwise means on the negative direction it is 0. On the negative direction it is 0. Otherwise, because it is having positive values for the signal where it is 1. So 0 to n. So from here 0, 1, 2, 3, 4. So let me write it in this fashion. Means till whatever value I write next, till 9, same value it continues. That's the meaning. I'm having amplitude 1, amplitude 1, amplitude 1, 1, 1. Here also 1, 1, 1. Until n, till 9 it is 1. Okay. So there onwards your values are 0. Values are 0. So here amplitude is 1, 1, everywhere 1. Till 0 to 9, I mean 0 to 9, in that range your amplitude is 1. I want to produce such signal using u of n. How to do it? Just write the mathematical function for this. U of n taking a step at 0. Now what I do is I need u of n till 9 only. After 9 I don't want it. After 9 I don't want it. Means at 10 I want it to get cancelled. At 10 I would want it to cancel. Fine. So at 10 I want to have one more signal which is taking a step. Which is that signal which takes step at n equal to 10? It is, I want a signal like this. I want some signal like this. I write the value of the value of the signal or the name of the signal later. From 0, 1, 2, I write in this fashion. Till 9 I want it to be 0. Till 9 I want it to be 0. At 10 and there on I want its amplitude to be 1. I want it in this fashion. So what is this signal called? What is this? It is taking step at 10. Write it in this manner. Write it in terms of u of n. U of n is taking the signal, same signal. This and this signal are same. Only thing is the signal that I have drawn just now is a shifted version of u of n. How many times this signal should be shifted to achieve this? It should be shifted 10 times. 10 times on to the right. What I'm doing is I'm taking this u of n. I'm taking this u of n. I'm shifting it right. I'm shifting this right by how many times? By 10 times. That's it. How to write it here? U of n minus 10. This is u of n minus 10. This is u of n. Now you just look at these two things. Okay. So I want to generate x of n. X of n says 0 to 9. I want to have amplitude 1. U of n has it. After that I don't need it. But u of n minus 10 has it. So what I do is I subtract u of n and u of n minus 10 with u of n. So let me check. I subtract u of n and u of n minus 10 in this fashion. So what happens? U of n, u of n, u of n is at 0, 1, at 2, 1, till 9 it is 1, or till infinity is 1, at 0, 1, at 1 it is 1, at 9 also it is 1. Same as u of n, it is continuing. Minus u of n minus 10 looks like this. So up till 0 to 9 it has got 0 amplitude, so it will be unchanged. It will be same as u of n. But after 9, at 10, here also you have amplitude 1. So when I have written dotted means throughout it is amplitude 1. So at 10, at 11 your amplitude is 1. Here also it is amplitude 1. So when I subtract it, the 10th, n equal to 10, n equal to 10, amplitude is 1 and 1, it cancels. N equal to 11, n equal to 11, amplitude is 1, amplitude 1, it cancels. Thereafter every time it cancels. Hence your given signal is achieved by a mathematical model. X of n is equal to u of n minus u of n minus u of n minus 10. So let me give an assignment for you before I conclude this class. assignment. U of t plus 1 minus 2 into u of t plus u of t minus 1. This is equal to x of t. I want you people to generate x of t. Okay. Similarly, x of n is equal to u of n minus 1 minus u of n minus 5. So these two are the examples that you are supposed to solve.